In this video, we're going to go through how to put in some of our matrix operations into MATLAB. So we're going to start with matrix addition. So let's start by putting in two different matrices. So I'm going to start with A equals, and I'm going to use example 2 under our matrix addition page. So I'm going to start my matrix with a square bracket, and then 0, 4 is that first line, semicolon, 1, 2, semicolon, 5, 6. I could put a semicolon here to suppress output. I'm just gonna not put it there so I can see this printed out. So my first row is 0, 4, second row 1, 2, third row 5, 6. So next I have my B matrix. Is first row is 1, 2, second row is 7, 3, third row, sorry, semicolon there, is 2, 0. So now I can add these two matrices up. So let's put this in a new variable. We can call it C, or we could call this, A plus B, and we have A plus B. We get to decide what we put on the left-hand side. That's the variable name there. So we could put any variable name here as long as it's a valid variable name. So last week we talked about, variable names can only have letters, numbers, and underscores, and they must start with a letter. So here A plus B, and we get 1, 6, 8, 5, 7, 6. So essentially that's just 0 plus 1, 4 plus 2, 1 plus 7, and so on. We can also do, I'm going to do a CLC here, A minus B. That's going to be A minus B. And just a reminder, our variables are case sensitive, so I can't put a lowercase b here. So if I did C is equal to A minus lowercase b, I'm going to get a error message that says undefined function or variable b, lowercase b, which means that I have not defined this lowercase b as a function or a variable. And then MATLAB typically suggests, did you mean this? Yes, I did. And then I'm not sure what just happened, but I'm just gonna CLC right there. Okay, so that's matrix addition, matrix subtraction. We can also multiply by a scalar. So I could do A times 3. So here we have A times 3. Note this is the same thing as 3 times A, which is 3 times A. So when we're multiplying by a scalar, that calculation is commutative. So that was matrix addition, matrix subtraction, and multiplication by a scalar value. Note each time for addition and subtraction, our matrices have to be the same size. If we try to add or subtract matrices of different sizes, we get errors, which there's a page after this one where I talk about common errors that you will see with our matrix operations. Next, we have matrix multiplication. So I'm going to start here with, let's call this one C. And C is going to be 4 by 1. So I'm just going to put 1, 2. So it has 4 rows, 2, 3, 4. 1 column is C. And D is going to have 5, 6, 7, 8. 1 row, 4 columns. So I can do C times D. So C is 4 by 1 and D is 1 by 4. So if I do C times D, I'm going to end up with a 4 by 4 matrix. If I do D times C, I'm going to end up with a 1 by 1. So let's just calculate that out. So I'm going to do C times D, and here I end up with a 4 by 4, and D times C will be a 1 by 1. Here, when I'm not defining what to store this in, remember it's going to store in this default A and S. If I wanted to say D times C, and now this value 70 is stored as a variable D times C over here in my workspace. So that's matrix multiplication. It goes a lot faster in MATLAB than it does by hand. Again, you will not need to do any of these matrix operations by hand. I do want you to understand the process, especially matrix multiplication. It's really important to understand how it works so that we can solve systems of linear equations. But you won't have to actually solve it by hand, because I'm teaching you how to code, not how to do math in this class. Okay, I recommend trying to type some of the other examples from the Canvas page into MATLAB, just to get comfortable defining matrices, multiplying them, all that jazz. So next we have element-wise multiplication. So to do element-wise multiplication, we need to have two matrices that are the same size. So if I look at this, A and B are the same size. And if I make this bigger, oh, never mind. So A and B are the same size. So I can do element-wise multiplication. So remember, A is this, B is this. So if I want to multiply 0 by 1, 4 by 2, 1 by 7, and so on, I will do element-wise multiplication. So that's A and then period times B. So that takes each element of A, multiplies it by the element of B with the same index. So 5 times 2, and then here we get 10. We will be using this a lot in this class, and kind of as we go on, we'll see more applications of this dot times. Okay, so next, let's do a system of linear equations. So the system of linear equations I am going to do, I'm going to type it out as a note to myself here, or a comment. So we have 2x plus y minus 2z equals 3. That's my first equation. We have 3 unknowns, which means I need 3 equations. So we have x minus y minus z equals 0. And here we have x plus y plus 3z equals 12. So remember, I'm going to set this up as a matrix AX equals B, where X, let's use a capital X there. So this capital X is what I'm solving for, and that's going to be my unknown vector. So that's going to be a vector where this X vector is equal to X, Y, Z. So X is going to be the first element in the first index, Y is going to be the second element, Z is going to be that third element. So for A, I'm basically taking the coefficients from this first equation for my first row. So I have 2 times X, 1 times Y, negative 2 times Z. Next row, 1 times X, negative 1 times Y, negative 1 times Z. The next row, I don't know why I put a bracket there, 1 times X, 1 times Y, 3 times Z. So that's my A equation. B is going to be the right-hand side of these equations, so it's going to be 3, 0, 12. So I have 3, semicolon, 0, semicolon, 12. And now I'm going to solve for this X. I'm going to use a capital X here. It's equal to, so it's going to be the inverse of A, which let's first get some help, I and B. So this is MATLAB help to help me figure out my inverse. So it says inverse of X is the inverse of the square matrix X. A warning message is printed if x is badly scaled or nearly singular. So that's if it can't find the inverse. And then we also see some other similar functions. Sorry, my cat's on my desk helping me out. So we have the inverse, so x is equal to the inverse of a times b. So this means that, let me put her on the floor. Okay, the joys of working from home. So we have x is equal to 3.5, y is equal to 1, z is equal to 2.5. Another way that we can solve for this, we can say x is equal to a, we put a slash that way, b. This is the same as this, it's just a different notation. So you can, once again, we can write this either way. So x equals inverse of a times b, or x equals a slash b. Okay, next let's talk about the dot product and how to put that into, oh, one more thing I wanted to talk about here. Let's look at what the inverse of a is. So we have a, that's what a is. So let's take the inverse of a. So that's our inverse matrix. And then if we do a times the inverse of a, we get an identity matrix. Here, there's a little bit of rounding error. This sometimes happens in our, when we're computing using computers. And we'll talk more about that later in this class. But this 0.0000 is essentially 0. It's just has a tiny bit of rounding error. So a times the inverse of a gives us an identity matrix, which has 1s on the diagonal. Trying to get to that dot product page. Okay, so next let's do a dot product. Oh, I didn't mean to clear, but that's, I guess we'll start over here. So a, let's call it a 1, 2, 3, 4. This is an example from the dot product Canvas page. So b is 5, 6, 7, 8. We can take the dot product, so we can say help dot. It says this is the vector dot product. It returns the scalar product of the vectors a and b, which note a vector is just a one-dimensional matrix. So it's a matrix that has only one row or only one column. A and b must be vectors of the same length. When a and b are both column vectors, dot AB is the same as a, oh, sorry, this is that. This is just another notation of how to do this using a little apostrophe. Sorry, that was not correct. This little apostrophe here is the transpose. I don't know why it threw me seeing it next to a multiply, but this a apostrophe means a transpose, which means we've taken a column vector and instead made it a row vector. And then you can do multiplication of that. So let's look at this. So we have the dot of a b is 70. Let's look at the transpose. So a transpose is 1, 2, 3, 4. So it's just taken the column vector and made it a row vector. So we can do a transpose times b, and that gives us that same answer, 70. We could also put, this is much more to type, but you could type the transpose of a times b. So this apostrophe after our variable name is just a shorthand way of taking the transpose, but you can always also type out the whole word transpose, which is a function, built-in function in MATLAB. Now let's define two more vectors. So let's say C is equal to 1, 2, 3. And then we'll do D is 4, 5, 6. Let's look at what cross is. So it says cross AB, so this gives us the syntax. Returns the cross product of the vectors A and B. It says A and B must be 3-element vectors. So we can do the cross product of C and D is equal to cross C comma D. We end up with -3, 6, -3. Okay, so that's our cross product. We can also take the determinant of a matrix using MATLAB, which again, I said this is a little beyond the scope, the math of how to find a determinant. And again, you won't have to find determinants by hand. We're always going to use MATLAB, but let's do help determinant. It says DET is the determinant of the square matrix X. Use cond instead of determinant to test for matrix singularity. So if you want to figure out if a matrix is singular, you can put COND, which gives you the condition number with respect to inversion, which for those of you who have taken linear algebra, right on, you can do this. But those of you who have no idea what this means, don't worry about it. It doesn't really apply to this class. So let's take the determinant of a matrix. The matrix is going to be 6, 1, 1, 4, -2, 5, and 2, 8, 7. So that determinant is -306. Now, I put the matrix directly into the function here. I could have just as easily said that A is equal to 6, 1, 1, 4, -2, 5, 2, 8, 7, and then said take the determinant of A, and it solves it that way. So you can do either way, where you first set the matrix as variable and then take the determinant of that variable, or directly plug in the matrix here. This is more of a style difference with coding, and you'll find as you progress in your coding kind of which one you feel more comfortable with. And we've already taken an inverse matrix and solved systems of linear equations. So I think that's it for this video. If you have questions, or if you had questions along the way, just a reminder that you can put those questions directly below this video as a comment. It's really helpful if you type the questions in at the timestamp where you had the question. That way I can see, what you have a question about and just type you a response. If it, is more than, or if it needs more explanation, I can always make a second video kind of explaining the answer to your question. So please, please, please be encouraged to ask questions as you have them, especially below the video here, or you can also use that Piazza page. The best way to get better at MATLAB is with practice. So I recommend, and I hope you are doing it as I was going through this video, following along and typing in each of these examples.